So we left off on Wednesday talking about resonance. And so we'll continue that discussion of resonance today, going through the rules of resonance. And then we'll talk about shape and geometry, topics that should be familiar from general chemistry. Then we'll get into a discussion of bonding. And we'll mention our two theories of bonding that we have, the valence bond theory, as well as the molecular orbital theory. And a reminder that today is the first day that we have the possibility of iClicker questions, so hopefully you have your iClickers here and ready to go. So when we left off on Wednesday, we had gone over rule number 3, which stated that the more stable resonance structure has the least amount of separation of charge between oppositely charged atoms. And we used methyl nitrite, one of our example molecules, as the sample for this. We showed you that we have this resonance structure that we can draw of methyl nitrite. And because the structure on the left has no charged atoms, by default, it has the smallest possible separation between oppositely charged atoms, whereas the one here on the right has a nitrogen in between our charged oxygen atoms. Okay? So what this means is that the true structure of methyl nitrite is a hybrid between these two, but the more stable structure, the one that's lower in energy, is what we call a major contributor. It contributes more to the structure than the higher energy minor contributor does. Okay? So knowing that, I've drawn our hybrid structure for us here on the board. And it has two bonds that are somewhere between a single bond and a double bond. So the oxygen-nitrogen bond here to the oxygen on the left, based on what I just told you in these two structures, is this bond going to be closer to a single bond or a double bond? I'll ask you another question if you're having trouble answering it. Which of these two structures contributes the most to the actual structure? The one on the left or the one on the right? The one on the left, okay? And so what is that bond in that structure, the one I'm referring to? It's a single bond. So that tells us that this bond here is going to be closer to a single bond than a double bond. It's still going to be in between, but if you had to give a number to its bond order, it might be like 1.1 or something like that, okay? So now you should be able to answer the other question. This bond here, is it closer to a single bond or a double bond? That one's going to be closer to a double bond. So this bond order, if we were going to number it, would probably be somewhere on the order of 1.9, very close to that of a double bond. And then we have these partial charges, a partial positive charge on the oxygen here that's bonded to the carbon, a partial negative charge of on the oxygen on the end. Is the magnitude of these partial charges closer to 0 or closer to 1? Okay, I hear a few people mumbling through your masks that it's closer to 0. That is correct. Why? Who would like to tell us why? It's closer to 0 than 1. Yes, please. Exactly. We look at our major contributor. We call this a major contributor and this a minor contributor. Our major contributor has no formal charges, so the actual charges in the hybrid should be close to 0. Very good. Okay. Any questions about rule number 3 or the example we've gone over? Okay, let's move on to rule number 4. This also involves comparing two or more resonance structures. The more stable resonance structure will have the negative charge on the more electronegative atom. And I've already drawn for you our example. This is a compound. We could call this a carbanion. It has a negative charge on a carbon. Who would like to raise their hand and tell me how we could draw a resonance structure of this compound? There is a way. Yes, please. Okay, so you're saying that we would take this lone pair on carbon and convert that into a double bond between the two carbons. And in order to do that, to not break the octet, we would have to convert the electrons in the carbon-oxygen double bond into a lone pair on the oxygen. And that's exactly right. We can do that. We've got to draw our double-headed arrows showing resonance. And so now we end up with a species looking like this. Based on this rule, which of these two resonance structures is lower in energy, the one on the left or the one on the right? The one on the right, exactly. Oxygen is more electronegative than carbon. So a more electronegative atom, since it pulls on its electrons more tightly, is more happy with a negative charge than a less electronegative atom. Okay? So that tells us this structure is more stable than that structure. So we can draw our hybrid. Our hybrid will look like this. We'll put our partial charges in. So which bond is closer to a double bond, the carbon-carbon or the carbon-oxygen bonds? Carbon-carbon is closer to a double bond, very good, because it is a double bond in our major contributor. Which of these partial charges is closer to 1? The one on carbon or the one on oxygen? The one on oxygen, exactly. Okay, so in the true structure of this compound, the oxygen will have a charge close to -1, and the carbon will have a small negative charge that is close to 0. This bond will be close to a double bond, but not quite there. This bond will be close to a single bond, but a little more than just a single bond. This species is referred to as an enolate. It is a very, very important compound. It's a reactive intermediate, and it is involved in a lot of the chemistry that we're going to learn in Chem 352M next semester. Okay, so you'll get very used to enolates and the two resonance structures of enolates at that point. Right now, we're not going to talk about its reactivity. We're just going to look at it in terms of the resonance that it possesses. Okay? Any questions about this rule? Now, please note that the corollary to this rule is not true. You might think that a more stable resonance structure would have a positive charge on a less electronegative atom. That is not the case. There's something else that comes into play when we have positively charged atoms. And you'll see that as you start to do problems and examples. We won't talk about it in the context of a rule right now, but as you work homework problems related to resonance, you'll see that. So the corollary is not true. This only applies to negative charges, does not apply. The corollary with positive charges does not apply. Okay, so let's look at our fifth rule. And our fifth rule says that each resonance structure must have the same number of electrons. This is how we like to abbreviate electrons. They must have the same net charge and the same number of unpaired electrons. And in almost all cases, the structures we'll be looking at will have either no unpaired electrons or just one unpaired electron. So the last part of this rule simply means that if we have a double bond between two atoms, we can't break that double bond and put one electron on each of the atoms. We can't unpair those electrons and call it a resonance structure. That would not be a resonance structure. That would actually be an entirely different compound and would be a very high energy compound, in fact, not something that we're going to be dealing with in this class. So we're not going to be unpairing electrons that are paired up when we're drawing resonance structures. We're also not adding or subtracting electrons. That's what the first two parts of the rule indicate, is that we have to have the same number of electrons as well as the same number of protons. We're not adding or subtracting either of those when we are drawing resonance structures. Those would be entirely different compounds. Any questions? Okay. Let's go to our sixth rule. The sixth rule, like the third and fourth rule, involves comparisons between two or more resonance structures. And it has to do with the degree of stabilization due to resonance. Okay, so I mentioned last time that when we have resonance structures, that imparts stability to a molecule. It indicates that we're able to delocalize electrons in that molecule, and that makes that molecule more stable. But how much more stable than if you couldn't delocalize electrons? That's what we mean by degree of stabilization. Okay? So the degree of stabilization, or how much stabilization we get due to resonance or electron delocalization, is greatest when our resonance structures are of equal stability. So we'll look at an example, the example that we started with, or not the one we started with, but one that we did talk about extensively on Wednesday, and that is our example of nitromethane. Okay. So here's one resonance structure of nitromethane. To make the other one, we simply exchange the positions of the single and double bonds between the nitrogen and the oxygens. Okay. Is there a difference in energy between these structures, or are they of equal stability? Equal stability, yes, thank you. Okay, these are, they're not identical to each other. The positions of those groups are, of the double bonds and single bonds are different, but they're not identical, but they're equivalent, and they're of equal stability, okay? So when we have this situation, we have the maximum amount of stability due to resonance, as opposed to the situation up here on the higher board, where we have resonance structures of different energy, a major contributor and a minor contributor. That still leads to stability. That still lowers the energy somewhat, but it's not going to lower the energy as much as if you have the resonance structures with equal stability. So if we were to draw our hybrid of nitromethane, it would look like this. Okay. So the hybrid, when we have structures of equal stability, the hybrid is exactly halfway in between them. And so that tells us that each of our nitrogen-oxygen bonds in nitromethane is going to be a 1.5 bond. Ozone was the same way with the oxygen-oxygen bonds. And that tells us that these formal charges on the oxygen are going to be -1/2, okay, because we have equal stability of these structures. And that means that nitromethane is stabilized more extensively to a greater degree by resonance than is our enolate, than is methyl nitrite. Okay? Any questions about that? Yes, Roger. Yes, so it's very difficult to draw lone pairs when you have partial bonds. Because when you have a partial bond, how many electrons are owned by each atom? It gets kind of fuzzy. So there's really no point in drawing lone pairs when you're drawing hybrids. So we just leave them out, which is why we don't use hybrids when we're drawing reaction mechanisms. Okay, that's a limitation of hybrids, is you can't really draw the lone pairs in because it's harder to count the octet when you have partial bonds. Okay, good question. Other questions? Okay, so the book gives you some good patterns of how to identify situations where you would be able to draw a resonance structure. So make sure you go through those. It'll tell you that if you have a lone pair adjacent to a pi bond, you can draw a resonance structure. When you have a positively charged atom that doesn't have the octet adjacent to an atom with a lone pair, you can draw a resonance structure. So things like that. So make sure you go through and read those and learn those. And then make sure that you are working homework problems that are asking you to draw reasonable resonance structures, because that's how you master these rules, is by applying them and working the problem. So it's very important to make sure that you work those homework problems. Okay? With that, let's move on to a discussion of the shapes of molecules. Okay? So our resonance structures and our Lewis structures, so far we've just drawn them flat on the board. But as you know, most molecules are not flat. They have three-dimensional shape, and that three-dimensional shape impacts their properties. And so it's important for us to understand the three-dimensional shapes of molecules. And there's two properties that we need to understand in order to do so, and that is bond length and bond angles. The bond lengths and the bond angles largely determine the three-dimensional shapes of molecules. So let's talk briefly about bond length and discuss periodic trends related to bond length. So let's look at the second row of our periodic table. Let's consider bonds of those second row elements to hydrogen. As we go from left to right across that second row of the periodic table, do the bond lengths between those atoms and hydrogen get longer or shorter? They're going to get shorter as you go from left to right. So bond length decreases across the periodic table. Who can raise their hand and explain why? It's important for us to understand why. Yes, please, in the back. Electronegativity, so it is correlated to that. As the electronegativity goes down, what happens to the size of those atoms as you go across? Yes? Absolutely. As we go across, you have more protons, which is why the electronegativity goes up, because it means it attracts the electrons more strongly. So the reason the bond lengths are getting smaller as we go across is that the size of those atoms are getting smaller. Smaller atoms will make shorter bonds. And the size is getting smaller because there's more protons and more electrons attracting each other within the same number of energy levels. And so those electrons are going to be pulled in more closely. Okay? Any questions about that trend? All right, what happens as we go down the periodic table? If we're looking at the halogens from fluorine to iodine, and we're looking at the bond lengths to hydrogen, are those bond lengths going to increase or decrease as we go down? Increase. Why? Atoms are getting bigger. Why are the atoms getting bigger? More energy levels, right? So we're adding an energy level each time we go down a column. Indeed, the atoms are getting bigger, so the bond lengths are increasing as we go down the periodic table, and that's also related to the size of the atoms. Our bond length range is fairly narrow. Angstroms is the unit we tend to use to measure bond lengths. On the low end, 0.74 angstroms is the shortest bond. On the high end, it's about 2 angstroms. So you have less than a threefold difference in bond lengths. So a fairly tight range. And more than the magnitude of the bond lengths, the important thing to note is the trends, to be able to look at two different bonds and see which one is longer than the other. Okay? All right, so that's our trend in regards to bond length. Let's talk about what happens or how we predict bond angles. Okay? So when we're talking about bond angles, not bungle, sorry. That was a combination of bond and angle, I guess. Sorry about that. Bond angles. The theory that we use is the VSEPR theory, one that you should be familiar with from general chemistry. Who would like to raise their hand and explain to us briefly what the VSEPR theory is? Excellent explanation. You said that the groups around an atom will spread out to be as far apart as possible. Why do they do that? They have electrons, yes. So when we're talking about groups around atoms, we're talking about two things. We're either talking about another atom that is connected via a bond, which has electrons in it, or we're talking about a lone pair, which is a pair of electrons. So every group around an atom has electrons, and those electrons want to be spread out as far as possible. They repel each other, okay? So VSEPR theory simply states that the groups around an atom will spread out as far as possible. There is one other detail related to it that we should go over, which is connected to the fact that electrons that are involved in a bond are not quite the same as electrons involved that are part of a lone pair in terms of how much they repel each other. Which ones repel each other more? The lone pairs repel each other more. So if we were to rank the types of repulsions, the repulsions between two bond pairs of electrons would be less than the repulsion between a bond pair and a lone pair, which in turn would be less than the repulsion between two lone pairs. And that has some consequences in that it gives us minor changes in actual bond angles relative to the ideal values that we would predict using the VSEPR theory. So with our second row elements, we're only going to have 2, 3, or 4 groups. We can't have more than 4 because that would require us to exceed the octet, which we can't do in the second row. So we're only going to look at VSEPR theory, or briefly review it as it applies to having 2 groups, 3 groups, or 4 groups around an atom. So a simple organic compound that has 2 groups around it, around the carbons, is acetylene. Acetylene is a gas that is used in the welding process. Here is the structure. Each carbon has 2 groups. Another carbon that it's triply bonded to, but that counts as 1 group, and a hydrogen. What arrangement in space will have 2 groups as far apart as possible? A linear arrangement. So we have a linear geometry in acetylene and any other organic compound where we have 2 groups attached to a carbon. So our bond angle is therefore 180 degrees. All right, let's look at a molecule that has 3 groups attached. Ethylene, this is another gas. Ethylene occurs in nature. It is a hormone that is released by plants that signifies the fruit to ripen. And it is also obtained from crude oil and is one of the most important, if not the most important, industrial chemicals used to make all kinds of plastics. Ethylene looks like this, C2H4. Each carbon has 3 groups attached, another carbon to which it is doubly bonded, and 2 hydrogens. What is the way that we can arrange three groups in space to get them as far apart as possible? Trigonal planar is what we call it. Okay, so they're all going to be in the same plane, and the arrangement they have in that plane is known as trigonal. Okay, and what is our bond angle for trigonal planar? 120. Okay, very good. All right. Now, four groups. We're going to look at methane. Methane is the principal component of natural gas. It's CH4, our simplest hydrocarbon compound. Now, when we draw methane, we're going to have to do something different than what we've done before, which is using wedges and dashes. Because what is the most stable arrangement of four groups in space? It is tetrahedral. So those four groups are not in the same plane. So how can we draw four groups that are not in the same plane on a chalkboard, which is flat? The way we do that is we use wedges and dashes. So this wedge, this solid wedge here, is indicating that that group is coming out of the chalkboard. And then these dashes here is indicating that that hydrogen is going back into the chalkboard. So technically, these two hydrogens should be eclipsing each other. If you made a three-dimensional model, and I encourage you to get molecular models, those will become very important when we get to chapter 4. But I strongly suggest you get some molecular models if you don't have them already. If you made a model, you'd see that this hydrogen is directly behind that hydrogen. It's eclipsed by the hydrogen in the front. But we couldn't draw it. If it was eclipsed, there'd be no way to draw it, right? And so the way we draw it is using these wedges and dashes. So that shows us that this hydrogen is behind that one. The arrangement we have in space is tetrahedral. And what is the optimal bond angle for something that is tetrahedral? 109.5. Okay. All right. So there are two terms that get used almost interchangeably, geometry and shape. Our book distinguishes between those two terms, but doesn't explicitly mention how it distinguishes between those two terms. But we're going to talk about that a little bit now because it's important to know the difference between geometry and shape when we're talking about molecules. Okay? So when we're referring to geometry, usually we're referring to the orientation at an individual atom. Okay? So what is the geometry of the carbon in methane? It is tetrahedral. Okay? Now in methane's case, you'd say that the shape is the same. The shape is also tetrahedral. But sometimes the shape and the geometry don't match. And that happens when we have lone pairs that are present. Okay? So a molecule you're very familiar with. What is the geometry of this oxygen atom? The geometry is tetrahedral. The geometry only relates to the number of groups. There are 4 groups around that oxygen. So we would say that the oxygen has tetrahedral geometry. What is the shape of the water molecule? The shape of the water molecule is bent. The lone pairs play a role in the bent shape. That's why it's not linear. But you don't consider the lone pairs when you're talking about the shape. You pretend they're not there. You kind of erase them from your tetrahedron, and that's how you end up with a bent structure. Okay? So looking at water helps us understand the difference, for purposes of this class, between geometry and shape. For geometry, we're going to keep the lone pairs in there. We're going to just be referring to an individual atom. For shape, we're going to be looking at a molecule, and we're going to leave those lone pairs out. Okay? Any questions? What is the bond angle in water? A little less than 109.5. Very good. Why is it less? you've got these lone pairs that repel each other more strongly. So that pushes those lone pairs further apart. And as a result, that squeezes those hydrogens a little closer together. And so that reduces the bond angle a little bit less than 109.5. I believe it's 105. I wouldn't expect you to have that memorized. As long as you knew that it was a little less than 109.5, that's good enough. Okay. Any questions about shape versus geometry? All right, let's talk a little bit now, before we go into bonding, about how we draw organic compounds. So on the board, so far in the class, we've been drawing them much in the way that they're drawn here in this left-hand column on this figure on the screen, where we're drawing out all the hydrogens, we're drawing out all the lone pairs. But what happens when we do that and we start drawing large molecules is it gets too big to fit on a screen or too big to fit on a page. So we have to have a shorthand way of doing it in order for it to be manageable, for us to be able to draw large molecules. And one way to do that is known as condensed structures. That's the term the book gives to it. These structures here on the right. So what we've done there, we're still drawing out all of our atoms, but we're leaving out most, if not all, of the single bonds. The only single bonds we're including are when we have a branch coming off of a chain. There's two ways to show that. One way is to show that branch, and then we don't show any of the single bonds that are in the chain. The other way would be to put parentheses around the branch, and then knowing that each carbon makes 4 bonds would allow you to figure out that this CH3 group has to be attached to this carbon and not to that carbon. Okay? But other than that, we leave out the single bonds. We use parentheses. You'll see we're omitting the lone pairs. We do need to know the lone pairs are there, but we don't need to draw them except when we're drawing reaction mechanisms. That's something we'll start to do in chapter 6 and then more heavily in chapter 7. Anytime we draw a reaction mechanism, we have to draw lone pairs that are involved in that reaction mechanism. But spectator lone pairs we can leave out. Okay? But we do need to know that they exist and that they're there. But to save space, we're leaving them out. And then you'll notice that we include carbon-carbon double bonds and triple bonds, but we're going to leave out carbon-oxygen double bonds. And the next page will show that. Okay? Here are condensed structures on the left, and those condensed structures represent these Lewis structures here in the middle, and they don't represent the compounds on the right. So how would we know? How would we be able to look at this structure, any of these structures here on the left, and know that they represent the compounds in the middle and not the ones on the right? Any ideas? How can you figure that out? Yes? Okay, so you're saying that these are more stable than that, and it would be the Lewis structure rules we would use in this case. And why? Why is that? Why would you say these structures are more stable, so these have to be the compounds? There's something glaring about each of these. Yes? Right. Carbon doesn't like to have lone pairs. Carbon has a low electronegativity, so it doesn't like lone pairs. And what else is there that's weird about these carbons with their lone pairs? Yes? It doesn't have the octet, exactly. So you'd go off the octet rule, which was a critical part of our Lewis structure rules that we went over. And so that's how you would know that these structures represent these compounds in the middle as opposed to the ones shown on the right. Okay? So those are known as condensed structures. You'll see them all the time in the book. You'll see them a lot on tests. You'll see them a lot on quizzes. So you need to be able to read them and recognize them and know what they are. But we go a step further than condensed structures, and we draw things that are known as skeletal structures. Skeletal structures, we leave out the carbons and hydrogens altogether. We draw these lines that are typically zigzag lines, and each vertex and each end of the line represents a carbon atom. And then each carbon atom forms 4 bonds. And so any missing valences are just filled in with hydrogen, but you don't write the hydrogens in. We do write heteroatoms. Heteroatoms are any atom in an organic compound that is not a carbon or a hydrogen. Carbon and hydrogen are the most common elements in organic compounds. Anytime we have other elements, we call those heteroatoms. In most cases, those are going to be oxygen, nitrogen, or a halogen. So we'll draw those in, of course. We will also draw hydrogens that are attached to heteroatoms. If we have an OH or an NH, we'll draw those hydrogens in. And again, like we did over here, we're going to leave out the lone pairs typically, although we'll need to show them if we're drawing reaction mechanisms and they're involved. So that would lead to us having structures much like this, okay? And the key to interpreting these structures is to know how many carbons there are in the chain and to know how many hydrogens are attached to each carbon. How many carbons are there in this compound? 6, very good, okay? Let's go left to right. How many hydrogens on this carbon? How many here? Here. Good, here. Here. Very good, okay? Now, when we draw the OHs, usually we draw them like this without a bond in between, but we could also draw it like that. It wouldn't really matter, but usually to condense things a little further, we just draw OH instead of O bond H. But of course, we have to recognize there is a sigma bond connecting those two elements together. So one that's difficult is an alkyne, a compound with a carbon-carbon triple bond, because we're used to seeing the zigzags and the rings and not something that's in a straight line. So let's try this one. How many carbons? 3 carbons, very good. How many hydrogens on the one on the right? 1. How many here in the middle? How many here? Excellent, very good. And then the last point we'll go over in regards to these skeletal structures is that when we have a charge, either a positive or a negative charge, if there's a negative charge, we do show lone pairs on carbon if there's a negative charge. We always do draw those. So maybe I'll switch it. I'll switch my example to one where we have a lone pair and a negative charge on a carbon. So a charge on a carbon replaces one of its valences, one of its hydrogens. Okay. So how many hydrogens on this carbon? Just 1, exactly. It's bonded to 2 different carbons. It has a lone pair or a negative charge, therefore it only has 1 hydrogen. Question? This one is a negative charge. Sorry, I'll try to make it thicker. But yes, that is a negative charge in this particular case. If it was a positive charge, the outcome would be the same. We would just have 1 hydrogen there. Okay. Are there any questions on our skeletal structures that we draw? You'll see these most frequently. When I draw things on the board, I'll usually be drawing them in the skeletal form. That's the form that most organic chemists use for drawing compounds. Okay? All right, so let's talk now about bonding. Our discussion of bonding is going to, we're going to start simple. We'll start with the simplest molecule in the world, which is H2. We just have 1 bond between 2 hydrogen atoms. And we're going to talk about the 2 theories of bonding, the valence bond theory and the molecular orbital theory, spending more time on valence bond, but just a little time introducing molecular orbital theory. But both of these theories are, what is an orbital? You can raise their hand and tell us what an orbital is. Anyone? Okay, Roger, go ahead. Okay, yeah, so it tells us where we would find the electrons. In order to tell us that, it has to be an equation. So I like to refer to orbitals as fancy mathematical equations. They're not some physical thing. They're just these complex, fancy equations. Okay? There's another term that's synonymous with orbitals, and that's wave functions. Physical chemists like to call them wave functions. Wave functions and orbitals are the same thing. But an orbital or a wave function is just the mathematical description of an electron wave. Electrons have the wave-particle duality, and when we're describing them in a mathematical way, we're usually referring to their wave-like properties. Okay? So in order to form a bond, we have to have orbitals on each of the atoms overlap with each other. They have to overlap in phase, which mathematically means they have to have the same sign. In any given region in space, the value of the equation will either be positive or negative. So that value has to be the same. And then when they overlap, we can form a bond, and we refer to that as constructive interference. Okay. Constructive interference is going to allow us to form a bond by overlap of two orbitals. Question? That's beyond my comprehension of physical chemistry, because it's been a long time since I took physical chemistry. So we're going to have a fairly simple treatment. And the rule we have in this class is if I don't remember or understand something, then you don't have to do it for this class either. Okay? So yeah, there is the squaring and the non-squaring, and we're talking about the one, not the probability one, but the one where you can have different signs, positive and negative. So when I think about waves, I'm not sure about you, but my personal favorite thing to do with waves is to go surfing. I used to live in Southern California. I don't have any surfboards anymore. I do stand-up paddleboarding now, but I used to go surfing when I lived in Southern California. And this picture I'm showing you right here is an example of constructive interference in the ocean. Okay? Many times when I teach classes, there are students who can identify where this picture is. And I'll give you two hints. It is in Southern California. And the second hint is look at what's in the background behind this wave. See if you can see what that is. If you live in Southern California, you might know what that is. But maybe we don't have anybody from Southern California in the class because no one's raising their hand. There was someone in the last hour. No. You don't know. Okay. This place is called the Wedge. This jetty here is part of the mouth of Newport Beach Harbor. Okay. So there's a place on the beach close to the mouth of that harbor at Newport Beach where you can get massively high waves a couple of times a year. And that is due to the phenomenon of constructive interference. What happens is when the waves are coming in at a certain angle, they will bounce off the jetty and head back to sea. If they hit another wave that's coming in and they're in phase, meaning that the peaks overlap with each other, you can get a double high wave, a wave twice as high as it ordinarily would be at that location in the ocean. Okay? And so a couple times a year, the conditions are just right for that to happen at this spot at the mouth of Newport Beach, and you get this constructive interference, this massive wave, 15 to 20 feet high. In the ocean, constructive interference leads to destruction of the surfer. But in molecules, when we have constructive interference, when we have orbitals or wave functions that are overlapping in phase, what we get is a bond. Okay? I've never surfed at the Wedge. I'm not a very good surfer myself. I'm more of a novice, but it is fun. Okay? So let's talk about overlap, constructive interference, and overlap of waves in molecules. So hydrogen. We have our two hydrogen atoms. What orbitals are involved? Just the s orbitals. So we have one hydrogen atom, right? The nucleus will just represent as a dot, another hydrogen atom. We bring those hydrogen atoms close together so that these orbitals that are of the same sign overlap with each other. We're going to get something that's going to be cylindrical in shape. And what is that cylinder? What do we call it? We can call it a sigma bond. Okay? It is a cylindrical bond that is centered on the axis between the two hydrogen atoms. Okay? And the electrons are most likely going to be found in the region of space between those hydrogens because they're going to be attracted by both of those nuclei. And so that's where the attractive force is greatest. We bring the nuclei as close together as possible in order to maximize those attractive forces. But if we bring them too close, then they would repel each other. So the ideal bond length is the one that maximizes the attractive forces between the electrons and the two nuclei and minimizes the repulsive forces between those nuclei. So in hydrogen, that's a fairly short bond length, the shortest, 0.74 angstroms. When we start to get larger nuclei, we have to have longer bond lengths. Okay? So that is our valence bond description of the sigma bond, the hydrogen-hydrogen bond in H2. Any questions? All right, so let's introduce briefly molecular orbital theory. And the book doesn't introduce MO theory until later on in the second half of the book. You've probably learned something about it in 111 and 112. We're just briefly going to go into it now in order to be able to compare it and contrast it to valence bond theory. Okay? So for our brief introduction to molecular orbital theory, the first point of molecular orbital theory that we're going to discuss is that electrons in atoms occupy atomic orbitals. Okay, those are abbreviated AOs. But then when we bond atoms together to make molecules, the electrons in those molecules no longer occupy atomic orbitals. They're going to occupy molecular orbitals. Those atomic orbitals don't exist anymore, okay? I should write this out before I abbreviate it. Molecular orbitals, or MOs, okay? So when we bond atoms together to make molecules, the atomic orbitals don't exist anymore. We've converted them into molecular orbitals. Molecular orbitals are generated by combining atomic orbitals. How do we combine mathematical equations? We add and subtract. So that's how we combine atomic orbitals. We add or subtract them. And then the number of molecular orbitals that we generate to make a molecule has to equal the number of atomic orbitals that were present in the atoms that we started with before we made that molecule. So with H2, how many atomic orbitals do we have in the individual atoms? 2 total. So how many molecular orbitals will we have in H2? 2, okay? So we take our atomic orbitals. First thing we do is we add them together. What do we get? Something that looks suspiciously like our sigma bond, because it is. It's just another way of arriving at the sigma bond. Adding these 2 atomic orbitals together to get something that we refer to as a sigma molecular orbital. And we're going to call that a bonding molecular orbital. Okay? So what's the other way we could combine these? We could subtract them. So to subtract them, we would need to change the sign or the phase of one of those orbitals. On the board, I'm going to represent that change in sign with these dashed lines. And so what's going to happen in the region where these overlap? Instead of constructive interference, it's going to be destructive. If we have a wave in the ocean, if we have a wave that overlaps with a trough, what happens? It's flat, okay? And so what we get when we overlap orbitals of opposite phases is they cancel each other out, and we get something that's referred to as a node. So this molecular orbital will have the dashed lines on the right hydrogen atom, the unshaded on the left, and then in the middle, we've got nothing. Sometimes we draw a dashed line indicating nothing, and that nothing is referred to as a node. So this is the molecular orbital we get when we subtract one of our 1s orbitals from the other. It's referred to as a sigma star molecular orbital or an anti-bonding molecular orbital. And we'll stop there. On Wednesday, we will explain the significance of those two molecular orbitals. And we'll go forward, going into hybrid orbital theory. You'll notice we didn't have iClicker questions today. I told you we wouldn't have them every time, but we will have them frequently. So please make sure you bring your iClickers on Wednesday. Please enjoy your weekend and stay safe.